When you flip a light switch, the lights turn on instantly, but the electrons inside the wire are moving forward extremely slow. So what's really happening? Let's look at it from a microscopic lens and what drift velocity is. So from a microscopic view, electric current is made of charged particles that are moving. That's what current is. In metals like copper, this would be free electrons bouncing around randomly, like gas particles trapped in a pipe. When an electric field is applied, they don't just rush through. Instead, they drift slowly in the opposite direction of the field. Fields going this way, they'll slowly move away. This average speed is called drift velocity, or Vd. And I'll go through a real-world analogy right after showing you the formula. We can derive current based on how many electrons pass through a cross-section. Cross-section being, if you had a pipe and you cut it in half, the open face, that's your cross-section area. The formula is current equals NEA drift velocity, with N being the number of free electrons per unit volume. E is the charge of an electron, which if you Google is 1.6 times 10 to the power of negative 19 coulombs. And I'll throw this on the free cheat sheet as well. A is the cross-sectional area of the wire, and Vd is drift velocity. This formula connects macroscopic current to microscopic motion of charges. And here's a real-world analogy. Imagine a pipe and it's full of ping pong balls, super full, and these ping pong balls are electrons. If you push one more ping pong ball in, one pops out the other side instantly. This is why lights turn on instantly. The electrons don't have to travel the entire length of the wire. They just nudge the next one forward, and then at the end one pops out and it powers your thing. Here's an example problem. Let's find the drift velocity of a copper wire. So you have a copper wire with a diameter of 3.2 millimeters, which means the radius is 1.6, which is 1.6 times 10 to the power of negative 3 normal meters. The current flowing through is 5 amps. And copper has one free electron per atom, which means one electron is allowed to move around in each atom of copper. The mass of 1 mole of copper, if you remember moles from thermodynamics, the mass of 1 mole, copper's molar mass is 63.5 grams, or in kilograms, 63.5 times 10 to the power of negative 3. The density is 8.9 times 10 to the power of 3 kilograms times meter cube, if you remember density from vacuum fluids. There's a lot of concepts coming in here, but we're finding the drift velocity. So getting the cheat sheet in the description is going to help you a lot because we're going to be using 3 formulas and they're all on there. Step 1, we need to find the free electron density, which is N. N is N over V, which is Na over the molar mass multiplied by density. And Na, if you remember from thermodynamics, is Avogadro's number, or 6.022 times 10 to the power of 23. It tells you how many atoms or molecules are inside 1 mole of a substance. So 1 mole of copper atoms would be this many atoms, or 1 mole of water molecules would be this many molecules. In our example, since copper has 1 free electron per atom, the number of free electrons per mole is the same amount of the number of atoms. It's a little bit complicated, but if you are fluent in your moles and your density, then you'll be fine. But this is equal to Avogadro's number divided by the molar mass, which is this value here, multiplied by the density of copper. You plug all of these values in, and your answer for N is 8.4 times 10 to the power of 28 electrons per meter cubed. That's the amount of electrons per unit of volume. Let's set this aside, make some space. So what's next? It's also good to know the cross-sectional area. Area is pi r squared when it comes to a circle, and radius is 1.6 times 10 to the power of negative 3, as we talked about here, giving us area as 8 times 10 to the power of negative 6 square meters. So that's the cross-sectional area here. Now we're ready to solve for drift velocity, because drift velocity, when you rearrange it from that current formula that we looked at earlier, with your excellent math skills, is current divided by our N value, electron charge area. Plug in your values, so current is 5 amps, which was mentioned at the start, and N, as we solved here, 8.4, 1028. The charge of an electron, 1.6 times 10 negative 19. And the area, which we can just plug in right there. Solve that fat fraction, and you get your drift velocity as roughly 4.6 times 10 to the power of negative 5 meters per second. This number is about 0.046 millimeters per second, which is slower than your fingernails grow. Isn't that interesting? Here's a recap. Electrons drift extremely slowly, but the current starts flowing instantly due to the chain reaction among the electrons. Just like that ping pong ball analogy. The formula is this, and it's on the cheat sheet in the description, and drift velocity depends on the size of the wire, the material, and the current. This explains why you cannot outrun a current even though the electrons themselves are crawling and slow.